Now that we have derived the formula for the Rydberg equation, or this formula for calculating the wavelengths in the hydrogen spectrum, let us just solve a numerical, because ultimately those are what are asked in our JEE mains and also sometimes in NEET. Okay, so what we are going to do in this today is that we are going to calculate the wavelength of third line in the Balmer series. So we have to understand a few things here. We have to understand what Balmer series is, and we have to understand what the lines mean. So the Balmer series is given here. What about the third line? So our first line of the Balmer series, so Balmer series happens when the electron jumps to the n equal to 2. So that is the final destination, n equal to 2. That is where it is coming. Okay, that is where it is coming. So this is the first line, this is the second line, and this is the third line. So for the third line, my initial position or my initial orbit is actually 5, and my electron is jumping to orbit number 2. So that is something that we just have to know. We have to understand what Balmer series is, what Lyman series is. So Lyman is orbit number 1, electrons coming to orbit 1, Balmer 2, Paschen 3, bracket 4. Okay, so that is something that we need to remember. From then, we can now compute the wavelength using our formula, the Rydberg formula. It is 1 by lambda, which is lambda is the wavelength, is equal to R is the Rydberg constant, into 1 by n1 squared minus 1 by n2 squared. So here our n1 and n2 are actually given. n1 is the final destination, it is the resting position. So that would be 1 by 4 minus n2 is 1 by, it is 5, so squared will be 25. Okay, so Rydberg formula, the Rydberg constant, we already know the value of this constant. It is 1.097 into 10 raised to power 7, but of course we are going to use a simple value. So what value do we use? We use a value of 1.1 into 10 raised to power 7, and then this becomes of course 25 minus 4, which is 21, and this becomes 100. Okay, very, very simple. 100, a factor of 100 came in, thankfully. It will simplify things quite a bit. And this of course is per meter. Okay, that is something that we have to understand. So we are this wavelength, if we compute it, it will come in per meter. Okay, that is where it will come in. So then I continue my work here because I have lack of space. So my lambda would actually be equal to, okay, lambda would actually be equal to 100. Okay, I just have to take reciprocal of both the sides, divided by 21 into 11. Okay, now what I am doing is that I am converting it into this 1.1 I have converted into 11, and at the same time this wavelength will be in meters. I am converting it into nanometers. So if I convert it into nanometers, this will be 10 raised to power 9, because that is what the nanometer means. And here, since I have converted this into 11, I will get 10 raised to power 6. Okay, so this, if you simplify it a little bit more, this will be 100 into 1000 divided by 21 into 11. From here, we can use the various techniques of approximation and we can mark the choices. But essentially, if you compute this will come out to be 434 nanometers. Okay, so this will be in nanometers. Okay, why is it in nanometers? Because I did the conversion. I used the factor of 10 raised to power 9 already. So hopefully this numerical is clear. It is very, very important that you are able to calculate it, and only thing you need to remember is the Balmer series, Lyman series, Balmer series, Paschen series, and we have a mnemonic on this channel, so definitely subscribe to this channel. And numericals practice many such problems. There are several such problems given on DoorstepTutor.com, okay, with solutions and explanations. Thank you.